Okay, a golf association requires that golf balls have a diameter that is 1.68 inches. To determine if golf balls conform to the standards, a random sample of golf balls was selected. Their diameters are shown in the table. Ooh, I want to see the table. Ooh, look at that. Beautiful. Because the sample size is small, the engineer must verify that the diameter is normally distributed and the sample does not contain any outliers. The normal probability plot and box plot are below. Let's just look at those. Okay, here's a normal probability plot. Since all the points are within those curvy bounds, then that means, sure, that's fine. There's no evidence to really suggest that the data is not normally distributed. Same thing goes for the box plot. There's no outliers. There's just whiskers that end here at those dots. There's no like outlier points that are far away. So yeah, the conditions are satisfied. There's no outliers. The data seems to be normally distributed. Really what we're saying is there's not evidence to suggest it's not normally distributed. Because when you technically do it, you do a hypothesis test where the null hypothesis is that the data is normally distributed, and you test whether the data would be very unlikely to occur given a normal distribution. But anyway, it's fine. We can continue. Do the golf balls conform to the standards? We're going to do a hypothesis test with a p-value and get the p-value. So let's copy this data, open it in StatCrunch. That's what the whole point of what I was opening the data table for. And let's stat. We're going to do a t-stat, a one sample t-stat with my data. Now, actually, you know what? I need to fill in the hypothesis. Let's just do that. So the null hypothesis is we're talking about the mean golf ball size. So mu equals, and mu, let's see, conforming to the standards. So they don't conform to the standards if they are bigger or smaller. Either one is no good. So I have to use not equal to in this case. And I'm going to do the same thing to fill in my hypothesis test here. Mu equals 1.68 and then not equal to. That's fine. Let's compute. Well, I got a test statistic 0.751. 2 decimal places would be 0.75. And then the p-value is going to be 0.46. 3 decimal places, 0.468. So let's copy that. Let's paste it over. That's pretty big p-value. There is definitely not sufficient evidence to conclude that golf balls do not conform. These golf balls are seem to be within the standards. Right? I would need this p-value to be extremely small, less than 0.01, to reject the null hypothesis, and it's not the case. Which of the following sampling is dependent or independent? Okay. Whether the following sampling. Okay, so a researcher wishes to compare personality types of brothers and sisters. Well, right away I can tell you, siblings are going to be dependent because the personality type of one sibling is probably going to have something to do with the personality of the other. So because they have something to do with each other, they're related. I mean, that's dependency right away. Sampling is dependent because an individual selected for one sample does dictate which individual is in the second because they're siblings. The people in one sample aren't like unrelated to the people in the other. You pair them up one by one. Is the response variable qualitative or quantitative? A personality inventory, the personality type. I mean, personality types, they're qualitative. They're not like a numerical thing. So it's qualitative because it classifies individual. Yeah, that's it. It's classifying them. Okay, a confidence interval for the difference of two proportions. So they're giving us the sample stats, and I just need to open up StatCrunch and go under Stat, Proportion Stats. Now I have two sample with summary data. In the first one, I have 371 out of 523. Second sample was 446 out of 581. I'm doing a confidence interval, and my confidence level is 90. Oops, 90. Compute it. And we got it. I have to scroll over to get it. Okay. This is my difference with 90% confidence. I need to, let's see, 3 decimal places. So negative 0.1018 rounds to negative, I'll just copy that part and put a 2 after it. Negative 0.102. For the upper bound, 3 decimal places, I need to round that up. So it's going to be negative 0.01015. Okay. That's it. A researcher studies water clarity at the same location in a lake on the same dates during the course of a year and repeats the measurement on the same date 5 years later. The researcher immerses a weighted disc painted black and white and measures the depth in inches at which it is no longer visible. The collected data is given in the table below. Complete parts A and B. Well, okay, so we've got paired data because you're taking it initially and then after 5 years, but it's the same day of the year. So they're paired. It's a paired data. Why is it important to take the measurements on the same date? Well, because because it takes care of other factors. Using the same date makes it easier to remember. No, it maximizes the difference. No, it makes the second sample dependent on the first. It's you're trying to take care of any other factors that might be at play. Yeah, I mean, so you want to do like you don't want to do like a bunch from one year in the fall and the other one in like the summer, because there's just biological things that happen during the course of the year. You want to, try to take those factors out of it so you can really just see if what's the effect of time for the 5 years difference. So does the evidence suggest that lake clarity has changed? Well, okay, improving. Let's open this in StatCrunch and do the test. Now I've got paired data. So under stat, I need to do t-stats, but I'm doing paired. Table 1, initial is the first sample, and sample 2 is after 5 years. I'm going to perform a hypothesis test for mean d equals that either equals 0. Now, okay, we have to be very clear about this. We're testing whether the clarity has improved. That's what we're asking. It says, does the evidence suggest that clarity in the lake is improving? Now, improving would mean that the second mean is greater than the first mean, because this is how deep you go until you can't see the little sinker thing anymore. So if the second mean is greater than the first mean, that means I should have a less than sign here. Less than. So I'm going to pick less than, which is like saying the first mean is less than the second mean. Yeah? Okay. That's the thing you got to be clear about. Well, let's see what we got. Well, we still get a p-value of 0.34, so we're not going to we don't reject the null hypothesis, but still we set it up correctly, so do not reject the null hypothesis. Remember, p-value has to be less than the alpha, 0.05, to reject, and it's not. Okay. Do people walk faster in the airport when they are departing, getting on a plane, or do they walk faster when they are arriving and getting off a plane? A reputable researcher measured the walking speed of random travelers in 2 international airports. His findings are summarized in the table. Okay, here's the table. Okay, so it's just a summary of this stuff. Now, is this an observational study or a designed experiment? It's observational, right? He didn't design it. He didn't put the people in one airport or the other. So it's an observational study since the researcher did not influence the data. Explain why it's reasonable to use Welch's t-test. Welch's t-test is just a two-sample t-test, okay, where you're not assuming equal variances. So are they large, independent? They're random and independent samples for sure. Are they large? Well, 35. We usually use 30 as like the cutoff for large enough. So yeah, you can say that they're random, they're large, and they're independent. They're large enough. Yeah. Do individuals walk at different speeds depending on whether they're departing or arriving? Okay, so now we want to actually set up the hypothesis test. The null hypothesis would be that the means are equal, and we're asking, do individuals walk at different speeds? So the alternative would be that they're not equal. They're just different means. There's no kind of bias on the alternative hypothesis of like, are they greater for departing or greater for arriving? But now we want to actually do the hypothesis test and get a p-value. So let's go to StatCrunch, go to stat, go to t-stats, a two-sample t-stat with summary. Okay, so I've got the sample mean, 258, the sample standard deviation, 54, and the sample size of 35. Second one, 272, 30, 35. I don't want to pool variances. As we said, this is a Welch's test, unequal variances, but that's a fine default to keep. And I'm going to keep things the same. I'm going to click compute, and I'm going to get a p-value, 0.1857. But I want to take only 3 decimal places, so I have to round that up, 0.186, 0.186, 0.186, oops, 6. Conclusion would be, do not reject the null hypothesis. There is not sufficient evidence, and everything else is gravy. There is not sufficient evidence at alpha equals 0.05 to say that travelers walk at different speeds. Yeah, this is greater than my alpha level, so I don't reject. There is not sufficient evidence. Okay? For the accompanying data set, this one right here, look at that, so cute, tiny, only 10 numbers. We want to get a scatter plot, correlation coefficient, and determine whether there's a linear relationship. So let's just pop that into StatCrunch, and let's do all of that. Let's start by making a scatter plot. Data, no, it's under graph. It's down to scatter plot. My x variable, I'll choose x, why not? Choose y for the other one, and I'm going to just click compute, and I'm going to get my little scatter plot. Now this is the shape I want. The now you'll notice here that all of these are from 0 to 10 on the x and the y axis. Just so that it looks the same, I'm going to go to options and edit the options actually. Oh, I'm sorry, it's not there. It's down at these lines here. I'm going to edit the y-axis and tell it that I want to go from 0 to 10. And I'm going to do the same thing for the y-axis. I'm going to go from 0 to 10. This is helpful because this makes sure that this has the same scaling as the little options that it gives. I'm going to, let's just see, I guess we'll just look at these side by side. You can see that it matches up with the fourth option. Okay, so that's good. Now, correlation coefficient. So here's what I'm going to do for this. This is a little different than I don't see my way of teaching. Don't look at the critical value tables at all. We're going to actually open a different website called StatPowers. I made this website, and we have tools in here for handling data like this. So I'm gonna go back and copy this data, these 2 columns of data. Hopefully it copies nicely. I'm going to go under 2 dependent paired samples. Clear this all out and paste. Here's my data, and I want to calculate. I'm going to look at the do a hypothesis test on correlation. Let's scroll down and you'll see what it says. So for a small correlation, it's this is a small sample size. My correlation coefficient 0.526 is, I'm going to move this over to the side so we can. Okay, so the correlation coefficient to 3 decimal places is 0.526. Oh, let's put in what's our alpha level? 0.05 is the traditional for calculating the significance of correlation. Now it's giving me the rejection region, which this is the critical value for this and this is what it's asking for. The absolute value, the correlation coefficient is, it's positive, and the absolute value of the correlation coefficient is 0.526. It is not greater than the critical value for this data set, 0.878. No linear relation exists. So this is a conclusion you want to make. If you opened up this table of critical values, you'd find the 0.878. That's the critical value for a sample size of 5. But anyway, I mean, if you don't trust me, 0.878, it's right there. Did you trust me? Well, I was telling the truth. But that's it. So the correlation coefficient 0.526 was positive. Absolute value doesn't change. Same thing. It was not greater than this critical value, so you can conclude there is no real linear relation, they say. Okay, cool. So consider 4 data sets shown in the accompanying table. 4 data sets. Wow. Wow, wow. Let's open everything in StatCrunch. We have all this data, all these data sets. We're going to find correlations, and we're going to find correlation coefficients, and we're going to create scatter plots. So let's just get to it. We're going to go to stat. We're going to we can do summary stats of correlation. Now under graph, I'm trying to think if there's a faster way to do it. I'm just going to do it this way. There's other ways to do it. Let's do summary stat of correlation. I'm going to pick x1, y1, and I'm going to see if there's actually a nope, no other options. Compute. The first correlation coefficient, let's just do them one by one. Let's just, yeah, linear correlation coefficient, we're doing 3 decimal places. Okay, 3 decimal places, 0.816 has to round up to 0.817. 0.817. Okay, well, let's go to edit, and let's pick x2 and y2. Let's compute 0.816. Okay, that's the same. The third one, the third data set, x3 and y3, 0.816. I think that they're going to play with us. Every one of them has the same correlation, and except they have very different scatter plots. x4, y4, can you guess? 0.816, actually 0.817. Now, they're going to have very different scatter plots, though. Let's do a scatter plot for the first data set. This is going to be under graph, scatter plot. Let's let's do x1 versus y1, compute it. It's this arcing shape. There's only one that looks like that. Edit, change that to x2, change that to y2, compute. This is kind of a vertical scattering. Looks like this. Let's do the third one. Edit. We're going to do x3 versus y3. And it looks like that. A line with one, I guess you call it a outlier. That point has what you call high leverage up there. This is the shape. And let's edit, change it to x4 and y4. And then you have these points here and that one point there. Now, since the shapes are so specifically different, I'm not bothering changing the scaling of my scatter plot, but I can recognize exactly what it is. Yeah, so I guess the point of this is that just because you have a high correlation, it doesn't mean that you have a linear relationship. Only this scatter plot here has what we'd call a linear relationship. The rest of them are, well actually the one with the outlier is a very good linear relationship, but this one's curved and this other one is just funky. So yeah,